Good morning, everybody, and welcome back to Abstract Algebra. Plan for today, we're going to finish off our discussion of Chapter 5 by talking about one more example of permutation groups called the alternating group. And then we're going to start talking about isomorphisms and homomorphisms, which are a Chapter 6 topic. As far as office hours go, I've got my usual ones, today and Wednesday. Today, I've got one from 2 to 3. Wednesday, I've got one 10 o'clock in the morning and 2 in the afternoon. Tomorrow, I've got office hours from 10 to 11 and 1:30 to 2:30. Dr. Gersel, Tuesday morning, says I have office hours till 11:30. And I've got a department meeting at 11 tomorrow, so I'm going to have to cut my morning office hour tomorrow a half hour short. As far as homework goes, don't forget, homework 4, due Wednesday. Also, you should figure out your exam. If you want to work with someone on the exam, you should figure that out in the next couple days. So here's the plan. Exam, going up on Wednesday, which means you'll probably get sent it tomorrow night or something. I've written the exam, but I want to go over it, make sure it's reasonable before I send it out. Exam's going to be a lot like a homework set, really. Except it's kind of a bit longer and kind of covers a bunch of different topics, not just the previous week. It will be comprehensive up to this point in the semester. By the way, cutoff point for the exam is today. With Chapter 5 stuff, there's not going to be any isomorphism, homomorphism stuff on the exam. Not that it really matters because you all can use your book, but just like with your homework, for the exam, you can use your book, you can use your notes, you can talk with one other person. Two other people, I suppose, but I have to be one. Any questions or comments? Okay, question came up in one of my morning classes. Am I planning on moving this class online? The answer is not yet. But don't be surprised if that happens. The kind of spiking COVID cases around campus. And if at any point you feel like it's not safe for you to continue attending class, let me know. Send me an email. Say, hey, I'm not going to be coming to class anymore. I'm just going to watch the videos virtually, and that is perfectly fine. You don't need to be sick. You don't need to be in quarantine. You can just tell me, Dr. Gersel, I would rather not come to class, and I will not take it too personally. Okay, what do you call a mathematician who really likes farm equipment? Call a mathematician who really likes farm equipment a protractor. Yes, we're recording. Okay, so I wanted to start off class today by finishing off Chapter 5, kind of this last packet on permutation groups. If you remember, we were talking about elements in Sn towards the end of class last time as being even permutations or odd permutations. Sn, again, being the set of permutations on the integers 1 through n. So we said that a permutation sigma in Sn is even if sigma can be written as a product of an even number of 2 cycles, and sigma is odd if it can be written as a product of an odd number of 2 cycles. So everyone remembers. Is that going to be an even or an odd permutation? If I cover up the 4, 5, is that going to be an even permutation or an odd permutation? Even? Well, let's see. I think if I cover this off, 1, 2, 3 can be written as 1, 3, 1, 2. Using that technique we talked about last time. For taking this cycle and writing it as a product of 2 cycles, just go first last, first second to last, first third to last, etc. And so here I count 1, 2, 3, meaning this product, or meaning this element is going to be an odd permutation. Whereas something like 1, 3, 7, 4, 2, you could write as being 1, 2, 1, 4, 1, 7, 1, 3. And then just for fun, 1, 5, 1, 5. And those two will cancel each other out. And we'll be left with 1, 2, 3, 4, 5, 6, an even number of 2 cycles. So the unintuitive thing that we saw in class last week is that a cycle with an odd number of numbers in it, like 1, 3, 7, 4, 2, will be an even permutation. And something like 1, 2, 3, 4 with 4 numbers in it will actually be an odd permutation. Because when you write it out as using 2 cycles, you get an odd number. So if you remember, at the end of class, I asked you to look at the back page and think about the questions. Do the set of all even permutations form a subgroup of Sn? And do the set of all odd permutations form a subgroup of Sn? And being my loyal, obedient students that I know you all are, I know you thought greatly about this over the weekend. Does anybody have any thoughts on which one they think forms a subgroup? Right?
Evens.
Why evens?
Because you'd have an even number of 2 cycles, so anytime you multiply 2 even quantities, you'd still have an even number of 2 cycles being multiplied. Whereas if you do odds, then adding 2 odds would give you an even number of 2 cycles.
Yeah, if you multiply 2 odd permutations, you're actually going to get an even permutation. And so the set of all odd permutations will not form a subgroup of Sn. Alternatively, the set of all odd permutations doesn't have the identity element, since the identity element is an even permutation. So if we start with the odds, they do not form a subgroup of Sn. And the quickest reason why is there's no identity element. Because we can just write the identity element as being, for instance, 1, 2, 1, 2. That's an even permutation, written as a product of 2 cycles. It is not in this set. And Fran pointed out, this set also does not have closure. In general, if you multiply 2 odd permutations together, you're going to get an even permutation. It does have inverses, though. Inverse of an odd permutation will be an odd permutation. So the odd permutations are out. Set of all even permutations, I claim, does form a group. And that's going to be called the alternating group. Even permutations in Sn do form a subgroup. And we're going to call that subgroup A sub n, the alternating group on n elements. So, I don't feel like writing it all out, but the inverse of an even permutation is even. The product of 2 even permutations is even. I should make that the exam question, maybe. I'm going to make that an exam question. I don't feel like spending too much class time. Let's do an example. If we were to take, if you recall, we found that all the permutations in S3 are the identity, 1, 2, 1, 3, 1, 2, 3, 1, 3, 2, what am I forgetting? 2, 3. We said that is going to form all of the elements in S3, the symmetric group on 3 elements, meaning the set of all permutations of the set 1, 2, 3. Which of these elements of S3 are going to be in A3? The alternating group on 3 elements. Can anyone give me an element in this list that is an even permutation? Okay?
L1.
Yeah. As we said, the identity element's always an even permutation. And if this is a subgroup, it better have the identity element in it. So A3 is going to contain the identity element from S3, as any good subgroup should. Megan?
1, 2, 3.
1, 2, 3. That can be written as 1, 3, 1, 2. So yeah, I think that checks out. Becca?
1, 3, 2.
And 1, 3, 2. Because that can be written as 1, 2, 1, 3, an even number of 2 cycles. And I think that's it. Hope you all believe me when I say these last 3 can be written as an odd number of 2 cycles. Namely, well, this is a product of 1 2 cycle, namely itself. Ditto, ditto. So it turns out this subgroup, A3, is good, or this set A3 is going to be a subgroup of S3. Set containing the 2 3 cycles and just the identity element. If we were looking at A4, we would also have to include things that can't be simplified into a single cycle, like say 1, 2, 3, 4, etc. Plus everything in A3. So 1, 2, 3, 4, 1, 3, 2, 4, 2, 1, 2, 3, 1, 3, 2, 1, 2, 4, 1, 4, 2, 1, 3, 4, 1, 4, 3, 2, 3, 4, 2, 4, 3. Yeah, those. We said the order of Sn is going to be n factorial. We talked, I think in Friday's class about why that's the case. Why do we know Sn always has n factorial elements? Anyone like to take a stab at to what the formula for the order of the alternating group on n elements is? Here's a hint. If n equals 3, it's 3. The order base of 3 is 3. Nope, not going to be n.
1/2 n factorial.
It is going to in fact be n factorial over 2. It's a good guess, Becca. It works in the case of n equals 3, but it turns out it won't work in any other case.
We're so freaking awesome.
Dr. Gerstle, what if n equals 1 and we look at the alternating group on S1? No, the alternating group on this set, A sub 1 is just going to be equal to S sub 1. A sub 1 does not have half an element in it. But in general, for n greater than 1, you'll get this n factorial over 2 formula. Any questions or comments? I have a question. Dr. Gerstle, why is this group called the alternating group and not just like the even group or something? It's given the name alternating group because if you look in the book, there's a horribly nasty way of defining this in terms of the sign of a permutation and blah, blah, blah. And basically it gets into, these are things which these are permutations which if you plug into a function, you get -1 instead of +1. And there's some alternating signs thing going on. Basically, if I wanted to spend an entire class defining the alternating group in a laborious way, I could define it in a way that would make the name alternating make a bit more sense. But I don't want to spend an entire class doing that. There is more information in the book, though, and there is a reason why it's called the alternating group, as opposed to just like the even group or something. Alternating group, by the way, is going to be very important for us later on in looking at some fun examples. Especially when we start looking at key normal subgroups of the alternating group, which is something we haven't talked about yet. Questions, comments, concerns? That is it for this packet. Congratulations. All right. So the next packet is going to be on chapter 6, isomorphisms and homomorphisms. And the question we're going to be looking at, the big question we want to answer in this packet is, when are 2 groups mathematically the same thing, even if they look a little bit different? And so here's my challenge to you. There are 3 groups on the front. Let's not I don't want to use my version because it has the solutions written on it. Pretend I'm holding up the packet. There are 3 groups on the front page of that packet. I'm giving you 3 groups with 4 elements apiece, along with their Cayley tables. Your job is to determine which 2 of these groups do you think are the same, even though they look a little bit different. They're just kind of relabelings of the same thing. Go ahead and take a couple minutes, think about that. I'm no longer going to say, talk to your neighbor if you both feel comfortable, or work with your neighbors because COVID, more of thing. That does not mean it's forbidden. I'm just not going to encourage it anymore. So keep that in mind.
Oh, I miss you.
Lauren, she misses me.
I think it's one.
I have not put my brain on this yet.
Is the middle one swapped instead of just like moving them on the left side?
If you want some hints, here's a hint to help you out. Which of these are abelian? Which of these are cyclic? And how many elements of each order do each of these groups have? For the 2 that are the same, these properties should all be the same. Delta, alpha, beta, alpha, delta, gamma, alpha, beta. Oops, I left off the bottom row. Shoot, if I don't encourage you to talk to each other, I have a much harder time telling if you're done. Go ahead and work another minute or so, and then we'll come back together and talk as a class.
Yes.
So there's a, they have orders four or three.
No, for the first one, 0 is square 1. 2 is 1.
Yeah, that's what I got. I didn't really measure it. Different.
That one's a bit different. It's all Greek.
It's all Greek to me.
Alrighty, let's go through and talk about these. By a show of hands, who thinks that the two groups that are the same are groups 1 and 2? 1 and 3. Alright, looks like common consensus. Why? You don't think the Greek group can be the same as the other ones? Let's see what happens when we go through and look at the properties. Group number 1. Is it going to be abelian? Show of hands, abelian? Cyclic? Alright, if it's cyclic, then what's it generated?
1.
1 plus 1 is 2, plus 1 is 3, plus 1 is 0. That'll do it. So our group can be generated by 1 and 3 as well, I believe. 3 plus 3 is 2, plus 3 is 1, plus 3 is 0. What group is this group table for? We've seen this group before. Back in the packet on cyclic groups.
Just addition mod 3 or 4 or something.
It is addition mod 3 or 4 or something.
Was that you?
It's not U10, because U10 would be 1, 3, 7, and 9. Actually, U10 would be U10 would be another group that is mathematically the same as this group, though. Fun fact. This is E mod 4Z. This is the group of integers under addition mod 4. This 4 is being treated like 0 if we say things like 1 plus 3 is 0 in this group. Okay, elements of order 1. Right.
0.
No. Some element that when you take that element to the first power, you get the identity. In every group, what element can you always take to the first power and get the identity? The identity. We have 2 generators, so that's going to give us 2 elements of order 4. And we are left with 1 element of order 2, namely 2. Turns out if we look at this third group, we get all the same stuff. It is abelian. It is cyclic. Anyone find a generator for the third group? Right.
B and D.
Let's see. B times B is C times B is D times B is A. So B will get you everything. If we did D times D is C, C times D is B, B times D is A, D will get you everything. Yep. So in the same way, we're going to get 2 elements of order 4 and a single element of order 2, namely C, because C is not the identity, but C squared does give you the identity. So yeah, groups 1 and 3 have all these properties in common. How about this Greek group? Is that an abelian group? You take the top right corner and you flip it over on the bottom left corner. Does everything match up? You betcha. Everything, or in other words, everything is symmetric along this line going from the top left to the bottom right. The betas match up, gammas match up, deltas match up, gammas match up, betas match up. So it is an abelian group. So this one's cyclic. Well, if we start taking elements times themselves, Alpha squared just gives us alpha, so the identity, so that's not going to get us the whole group. Beta squared is going to give us, well, the identity, so that's beta's not a generator. Gamma squared, oh, that's just alpha again, that's not that's not a generator. Delta squared, that's also the identity. Everything in this group has, other than the identity, everything in this group has order 2. Because if you square anything in this group, you're going to get the identity. You can't keep multiplying an element over and over by itself and hope to get the entire group. So, you all were right. Groups 1 and 3 are mathematically the same. They have all the same basic properties. They're both abelian, they're both cyclic, they have the same number of elements of each order. They have the same number of subgroups. They have, fill in the blank, they're basically, for all intents and purposes, the same group, except I took the first group and replaced all the numbers with letters. And even though the elements may look like different things, letters instead of numbers, they're actually, what you call the elements doesn't really matter for an algebraist perspective. Algebraist doesn't care what the elements look like. They could be letters or numbers or matrices or emojis. You could have formed a group with these as our group elements, and if it had the same basic behaving Cayley table as this one or the first one, we would still say mathematically they're the exact same group. The elements it's just got the same group but with a facelift to it. Has all the same properties that we would care about, like is it cyclic, is it abelian, how many elements of order 1, 2, and 4 are there, etc. So before I erase this, fun fact, I had a TA in grad school, and no, this was not Dr. Gabler. That was a different TA. I had a TA in grad school who would call every Greek letter delta. So we would look at something like this, and he's like, yeah, so if you multiply delta and delta together, you get delta. And it was the most confusing thing. I don't know why he did it that way. I should have pretended it was Dr. Gabler. That would have been a juicier story. At some point, Dr. Gabler learned the Greek alphabet has more than one letter in it. Okay, so we all kind of have so I did this to kind of give you an intuitive sense of what does it mean when we say two groups behave the same way or are the same mathematically, even though they may look a little bit differently. So what we're going to be doing for the rest of this packet is we're going to be defining terms and looking at examples of how can you actually mathematically prove two groups are mathematically the same. And ultimately, what we're going to be building up to is defining a specific type of function called an isomorphism, where if you can define a function between two groups that's an isomorphism, that proves the two groups are mathematically the same. Before we do that, we need to talk about homomorphisms. So I'm going to flip to page 2 in the packet. So a homomorphism, or a group homomorphism, I should say, is just going to be a function that goes between two groups that has an interesting property to it. So if G1 under star and G2 under fancy times are groups, a group homomorphism from G1 to G2, let's say phi from G1 to G2, is a function that satisfies for all elements in the first group, for all, I'll say little g and little h in G1, we want it to be the case that phi of G star h, little g star little h is equal to phi of G, fancy time symbol, phi of h. So what does this mean? It's a function that goes from one group, G1, to the other group, G2, And we want it to satisfy the property that if we were to multiply the two elements in the first group together using the first group's operation and then apply the function phi, we want to get the same output as if we had taken phi of g and phi of h separately, taken our L, and then done the group operation from group number 2. So if we put that in words, we can say we always get the same thing. If we multiply in G1, then do phi, versus if we do phi to both elements, then multiply in G2. So basically, it's saying the order doesn't matter. If you do the first group operation, if you do the group operation and then take phi, you get the same thing as if you take phi separately and then do the group operation. But since G1 and G2 may be different groups with potentially different group operations, we want to get the same thing using the group operation from G1 versus the group operation from G2. Questions or comments? Let's do an example. It says from Z to R. Nah, let's do this. D3 to GL2R. Phi of x is equal to 1, 0, 0, 1. This is a function that's going to take every element in the dihedral group D3 and map it to the same matrix in GL2R. It's going to map it to the identity matrix. I claim this is going to be an example of a group homomorphism. So why is that? Phi is a group homomorphism. Well, it turns out that if we take any two elements in our first group, what do you want to call our two elements in the first group that are arbitrary? Arbitrary elements. Don't use specific ones. A and B. So if we take A and B, both being elements in the first group, D3, if we were to take phi of AB, if we were to multiply the two elements in D3 together and then apply the map phi, well, if phi of everything is just the identity matrix, this is just going to give us the identity matrix. Because we say phi takes everything in D3 to the identity matrix. And we also are going to notice that if we were to take phi of A and phi of B separately and then multiply them together, well, we're going to get the identity matrix times the identity matrix. And what do we get if we multiply the identity matrix together twice? That's just the identity matrix, which is equal to just phi of the product. If we were to take our two elements in D3 and multiply them using our group operation from D3 and then apply the map phi, we're going to get the same thing as if we took phi of A and phi of B separately and got two matrices and then multiplied those matrices together. Phi of G star H is equal to phi of G fancy times phi of H. where in this example, this star here, star is going to be transformation composition, composing two symmetries. I should say symmetry composition. Our operation times with a star around it is going to be matrix multiplication. But if we composed the two symmetries A and B together and then applied the map phi, we're going to always get the same thing as if we took phi of A, phi of B separately, got matrices, and then did matrix multiplication to phi of A and phi of B. This would be an example of a group homomorphism from the dihedral group D3 to Gl2R.
Does the output of B have to be an element in either of the two groups, or can it be anything?
They have to be an element in the two groups, because otherwise, if like A and B are not elements in D3, well, our function only takes elements of D3 to elements of Gl2R. If A and B aren't in D3, then phi of A and phi of B aren't going to be defined to be anything. So whenever we take elements G and H and we're checking for a group homomorphism, we always need to start with two elements that are in the first group, that are in the domain of the function phi, in other words. Good question. Any other questions? All right. What if we took the map I don't know. Let's find one in the packet that's not. Let's take the function f from the integers to the real numbers, where we say f of x is defined to be equal to the absolute value of x. That's a function that takes in integers and spits out real numbers. That takes every integer to the absolute value of that integer. What would we get if we took f of 1 plus negative 5? Well, we would get f of negative 4, which is going to be absolute value of 4, which is 4. On the other hand, if we took f of 1 plus f of negative 5, we would get absolute value of 1 is 1, absolute value of negative 5 is 5, and we would get 6 this time. So what does that tell us about the absolute value function as a function from the integers to the reals? No, Nick, it doesn't tell us anything?
It tells us it's not a homomorphism.
Yeah, this is going to tell us, since we found two elements in the first group, such that f of a plus b is not f of a plus f of b, that tells us this cannot possibly be a group homomorphism. Since f of 1 plus negative 5 does not equal f of 1 plus f of negative 5, f is not a group homomorphism. Oftentimes you'll just see hom written out for homomorphism. In order for it to be a homomorphism, it needs to be the case that if you do operation in first group followed by function, you get function followed by new group operation every single time. If it works in some but not all cases, it's not a group hom. Just because f of 1 plus 2 is equal to f of 1 plus f of 2 doesn't mean there aren't some other examples where if you do this in different order, you don't get the same thing. Whereas for something that is a group homomorphism, it needs to work regardless of which two elements you started with. It needs to work for two arbitrary elements in the group. That, by the way, is why I didn't want you to pick R and S, because just because it works for R and S doesn't mean it couldn't work for something else. But R and S would be an example of this general property. Questions or comments? All right, pages 2 and 3 of this packet have lots of examples and counterexamples of homomorphisms. Take a few minutes, See if you can determine which are which.
So, that's compensation.
There's a typo in this packet on the second page of these. It says alpha from GL2R to R. Put a little time symbol on that R. We're gonna look at the non-zero reals under multiplication. Okay, that's a typo in the packet. Got it?
So does the homomorphism have to form a subgroup in the new group? Like, does the
Homomorphism is a function,
Does the image of the homomorphism have to form a subgroup?
as we will
That's
see.
something we're gonna, okay.
And for that matter, the kernel of a homomorphism is also going to form a subgroup of the
Right.
original. All on the same lines.
Because we're dividing it, it doesn't work. If you multiply.
You see you see the term kernel of a map?
That's what I'm.
Or, sorry, I was still thinking about the,
Does it have to do with?
what was the first question I asked, because I was gonna ask about the, whether
So
it's
yeah, so we
computed
have to be in addition.
real time or if it's just the
What do you
real
think
time.
so?
Wait, for which one?
For this guy that you just corrected.
Uh,
I was gonna say it does
That's what I guess I'm
It's
Uh,
that one hundred, but it's not a homomorphism, it's not one.
This one?
Well, if it's not a homomorphism, then it doesn't need to form a subgroup. If it is, then it should, and,
So this doesn't apply, so it would be.
I think that one is, I think for alpha, with the fixed alpha, it should.
Oh, well. The third one on the first page is not, right?
So the first two
Yeah,
operations
but
are
you just did
addition
that,
for
yeah.
integers, but
Yo,
is the second one always gonna be addition or
I said no.
for the real, if we're talking about the real numbers as a group, the all reals, including
why is
zero,
that?
then it's addition.
Okay.
Yeah.
R star, if we're taking away zero, then R times
So
the
is
group
that what
under
the X
multiplication.
means?
Yes.
But not under division.
No, the X means it's non-zero and real.
So why do we know it's multiplication?
This
We're
is testing
looking
my
up.
memory of these. more than I thought.
You know it's multiplication because that's what it always is.
Okay.
For which one are you looking at, Gabe?
The second one on page 2.
Okay, so it still works.
It's a multiplication because the
So
non-zero
that one still
reals
works.
only form a group under multiplication. They don't form a group under addition because there's no identity element.
That makes sense.
Oh, yeah, because it's adding, oh.
It
And then the
is
next one, I didn't figure that one out.
It has to get, because no one
Gotcha.
determines, like, have that property.
This one probably won't though.
This
This
Did
person
you add it?
has- Yeah, I need to write out the.
You added it to
Yeah.
multiply.
I don't know.
I don't remember.
It's hard, until you work with these a whole lot, it's hard to sometimes remember what's our group operation here?
I don't wanna.
If you're ever uncertain about what is the group operation, you're welcome to ask.
I remember the group operation, I don't remember what the relationship for determinants, like how you can add or.
Right, like what happens in the
Yeah, this is
determinant, we
not-
can
Turn
add or
Time determinant equal determinant.
Yeah, perfect, then.
I think the last one doesn't fit, right?
I don't think so.
Yeah.
Does that answer your question? Determinant breaks up nicely over products, but not addition.
Perfect.
That's why I needed to fix that example.
Exactly how we.
I don't think you could ever.
Unless one of them is zero,
Yeah, it's the deal for.
because.
I start looking at
Dang it, uh-oh, that's a group we just met.
I know.
I will say this, SN and AN, same group operation, just you compose the two permutations. The image of the.
Well, so I was just thinking, if it's not a punctured real plane, then it's gonna be,
I gotta say,
that means it's gonna be addition is your.
I'm not a mathematical guy who's not.
Right.
Until you take your topology before this.
Oh, I don't know. There's, I think there's a determinant.
So,
basis that
the image is
that
just gonna be the entire group.
The determinant of AB equals determinant.
Yes, that is definitely.
Are you talking about like what GL2 are?
Well, so
Definitely.
all I was thinking is,
So then-
I wanted to do this.
Right, well, what is,
I was
I
like,
have
that's
anything
right,
in
I'm so confident.
I know, because it feels right, like I know there's something like
I
this.
swear to God.
So it's
Uh,
I
I think it works because it's
That makes sense, yeah, I know there's
operating.
definitely one of them, and it would make sense for addition.
Okay.
Maybe
Well,
just, maybe.
Here's the
Yes, yes, zero, and then it has to be
Yeah.
So that's
Yes,
fine.
if I just, okay, I got you, yeah, if I just said is the map from GL2R to R, the group of all reals under addition.
I feel like you guys are just
That
more
one.
than
That's what I.
Okay, got it, sorry, I was misunderstanding your question, so you're phrasing it in a very philosophical way, so I thought about the logic.
Oh,
We're
right.
awesome. No worries, I get what you're going for.
It's too fresh.
It's the same one, no.
Right, so it would be even, or would it be the same thing?
Winking at all the people who promote stuff.
Think to think, if it did all work out that way.
The square makes me uncomfortable that it's like a square around whatever the operation is, or an operation in the square.
Composition,
Thank you.
it's the one that says 1, 2 times 1, 3 is just 1, 2, 1, 3, the product of those two cycles.
Yeah, but it's, yeah.
Alright, let's come back together for a second.
Something else.
So, I think we're ready to start talking through some examples. And by we're ready to, I mean in 47 hours from now because class is over. Plus or minus minutes. So we'll start off, if you haven't looked through all these examples, I encourage you to do so before class on Wednesday. Once we start Wednesday's, at the start of Wednesday's class, we'll go through each of these examples and see what you all think about them. And then from there, we'll start talking about some properties of homomorphisms and eventually define a special term called isomorphism, which is a type of function that's going to tell us our two groups are the same. Have a good rest of your day.